Hey everybody! In this video, we are going to talk about the first law of thermodynamics. But before we begin, I want to clear up a misconception. Remember how I said that we can essentially think of enthalpy H as the internal energy of a system? Well, when I said essentially, I meant that the enthalpy closely resembled the internal energy. But to tell you the truth, internal energy is not exactly enthalpy. Instead, internal energy actually has its own symbol, E, which stands for internal energy. As you remember, internal energy combines every form of energy, from heat energy to the potential energy to even the kinetic energy of anything. So, yeah. Now let's talk about what the first law of thermodynamics states. The first law of thermodynamics states that the system's change in internal energy is equal to the sum of the work and heat. And keep a note that work and heat are two ways in which energy can change, either through the transfer of heat energy, as is with heat, and either through maybe the transfer of energy via moving something, and that would be considered work. So when energy changes, it can either change into work or energy, and in the end, the energy is not created nor destroyed. So maybe I should write neither, because that is more grammatically correct. Alright, so if you remember, heat is the flow of heat energy between two systems at different temperatures, while work is literally anything else. For example, moving a car takes work because you are putting energy from your hands to move the car and give the car some kinetic energy. So in chemistry, we are going to look at a piston system on a closed container filled with a bunch of gas, and we are going to move the piston up and down. So, in this closed container with a piston, if a piston pushes down on a closed container with gas, the volume decreases, as shown over here. Work is done on the system, which is the gas, so work is going to be considered positive. Now, if the gas pushes on the piston, then the volume will increase. Work is done by the system, so the work is negative. So be sure to know how to differentiate between work being positive and negative depending on the situation. So let's look at this cool equation. It states that work is equal to negative times pressure times the change in volume, and the change in volume is just the final volume minus the initial volume. So let's prove why this equation makes sense. So in the first situation, since work is positive, then delta V is going to be negative, since remember, decreasing volume is when work is being done on the system, so the change in volume will be negative, and pressure will always be positive. So since delta V, which is this one, times P is going to be a negative number, then we need a negative sign in front to make the delta V times P positive again to reflect the positive work done. So hopefully that made sense. So before we continue, note that E, like H, is a state function because they are both forms of energy. So now let's try to relate enthalpy to internal energy through the first law of thermodynamics, which stated that the change in internal energy is equal to the work plus heat. So we write that equation out, and we can substitute Q for delta H, since they're essentially the same thing, but without the per mole thing, which the delta H has while the Q doesn't, minus PV, and the minus PV simply comes from the fact that W is equal to negative P delta V. So looking at this equation, we can rearrange it and say that E plus P delta V is equal to delta H, move the equation around, and we get delta H equals delta E plus P delta V. And a good way to memorize this equation is to remember that heat is spelled as this, and notice how H and E represent those, and I don't know what these represent, but just know that the PV is after. So, nice way to memorize this, and let's continue. So, we know that PV equals nRT, and the R is usually 0.0821, but in this case, we are going to substitute PV for nRT, and we get delta NG times RT, and this time the R, since everything is in terms of energy, the R will be 8.31 joules per mole times Kelvin, or 8.31 times 10 to the negative 3 kilojoules per mole times Kelvin. And the reason why it's 10 to the negative third is because when you convert joules to kilojoules, you multiply by 10 to the negative third. So, misconceptions cleared, and let's now continue. So, the temperature should be in Kelvin, and delta Ng just means the change in the moles of gas for a reaction. So, the moles of gas in the products minus the moles of gas in the reactants will give you the delta Ng. So, now that we have these nice equations, we can talk about how these equations are used. So, we typically use this equation when we're dealing with anything that doesn't have to do with reactions. And we use this one for reactions. And we will be focusing on H equals E plus nRT, and I forgot to say the deltas, but you get the point. And let's now talk about this equation, which is the one before. This can be kind of simplified to this, and this is actually the true definition of enthalpy defined by scientists across the world. So enthalpy is equal to the internal energy plus the pressure times the volume. So that's pretty cool. Let's now continue and try to do a practice problem using the things that we learned. So let's look at this reaction. C2H2 plus 5/2O2 becomes 2CO2 plus H2O. And notice that these are all gases. They give us the delta H of the reaction, which is negative 1255.5 kilojoules per mole of reaction. So we need to find the delta E, assuming that the standard condition is at 32 degrees Celsius. And remember that the standard condition is usually at 298 Kelvin or 25 degrees Celsius, but this can vary. But one thing that has to stay constant is that it has to be 1 atm and 1 molar. But the temperature can change, and we tend to measure things at 25 degrees Celsius, which is why things that we see with the not symbol are typically thought to be at 25, but since I specified it to be 32, we are going to use 32. So we write out the equation that we use for reactions, H equals E plus nRT with the delta symbols, and we have to calculate the change in the moles of gas. So the change in the moles of gas will be, on the right-hand side, we have 3 moles of gas. On the left-hand side, we have 1 plus 5/2, which is 7/2 moles of gas. So 3 minus 7/2 is negative 0.5 moles, which is delta Ng. And now we could actually substitute everything. So the delta H is in kilojoules, and this is equal to delta E naught plus negative 0.5 moles, our change in moles of gas, times 8.31 times 10 to the negative 3 kilojoules per mole times Kelvin. And we use this one because we are matching the units. Since this is in kilojoules, this should be in kilojoules as well. And this would be in Kelvin, so 32 plus 273.15 would be 305.15. And doing some algebra, we get that delta E naught is equal to negative 1.25 times 10 to the third kilojoules per mole of reaction. And notice how the delta E naught and the delta H naught are pretty close to each other, while this one is probably just 1 kilojoule off from this one if we don't count sig figs. And because of that, we can conclude that delta E and delta H are really similar, but they're not exactly the same thing. So before we end this video, I want to do a little fun physics activity that proves that the pressure times volume is equal to energy, or work in this case. And at first you might be wondering, how can pressure times volume be equal to energy? That does not make any sense at all. Well, I'll show you that it makes sense using some unit analysis, and if you haven't taken physics before, then I don't recommend you follow this, unless you really want to, of course. So, P is pressure, and that is in SI units, pascals, and the SI unit for pascals is newtons per meter squared, and simplifying that to the fundamental SI units, we get kilogram meters per second squared times meters squared, and simplifying this by canceling out the m on the top, we get that the units for Pascal is going to be kilogram per second squared times meters. Now, volume is simply just meters cubed, since, a cube is technically a volume. So, work is defined as joules, and joules is kilogram meters squared per second squared. And now we have to prove that the units for energy is the same as the units for when we multiply pressure times volume. And doing that, we get kilogram meters squared per second squared is equal to kilogram per second squared times meter cubed. And we get that on the right-hand side, it is going to become kilogram meters squared per second squared. And notice that the units on both sides match. So we just proved that pressure times volume can potentially give us energy. So that's pretty cool. And that's all for this video. Have a nice day.